Today we are looking at question 5, which is about optimization. Consider three agents, j is equal to 1, 2, and 3, who each have an opinion, sigma j, about an issue, who all have the same evidence eta and whose utility functions are given by this function over here. The term proportional to sigma describes that these agents prefer to agree with their neighbours. Part A is telling us to find first order conditions for the optimum opinions of agents 1, 2, and 3. To begin this question, I am first going to write down the function for agent 1. In order to do this, we sub in j is equal to 1. This gives us eta sigma 1 minus r over 2 sigma squared 1 minus mu over 2 brackets sigma 1 minus sigma 2 all squared plus sigma 0 minus sigma 1 all squared and close bracket. So this is our utility function for agent 1. If we now do the same for agent 2, we will sub in j is equal to 2. So wherever we see j, we are just going to sub in 2. When we do this, we get this utility function for agent 2, and if we just do the same thing for agent 3, we will have to sub in j is equal to 3. And this is what we get. So now if we go back to the utility function, our utility function is saying that when we work out the individual utility functions for agent 1, 2, and 3, we need to sum them together to find this whole utility function. So u, which is a function of the vector sigma, is going to be equal to u1 plus u2 plus u3. So these three equations. What we are now going to do is work out the first order conditions of this utility function. If we work out the first order condition for agent 1, it means that we will differentiate this utility function with respect to sigma 1. What that means is we now need to look at which of these have sigma 1 in them. So we have eta sigma 1, r over 2 sigma squared 1, all of this and all of this, and we also have this. So if we differentiate this, we get eta minus r sigma 1 minus mu brackets sigma 1 minus sigma 2, and then plus sigma 0 minus sigma 1, and then minus sigma 1 minus sigma 2. Cool. If you couldn't follow along with that. So when I differentiate this, if we focus on this bracket, we will use chain rule, and we have 2 brackets sigma 1 minus sigma 2, and then we differentiate what's inside the bracket. So when we differentiate sigma 1, we just get 1, so we don't need to write that. If we now multiply this with minus sigma 2, minus mu over 2, we will get minus mu over 2 sigma 1 minus sigma 2, which is what we got over here. If we do the same thing over here, we get 2 sigma 0 minus sigma 1. Differentiating what's inside the bracket gives us minus 1, so we get minus 2. Multiplying this by minus sigma 2, we get 2's cancelling out, and positive mu, which is what we got over here. And this is the exact same as this. Cool, hopefully that makes sense. If we now expand the brackets and collect all the like terms, we have eta r sigma 1 minus 3 mu sigma 1. That's me collecting this term, this terms, and then this term. So that's multiplied by that. And then we're left behind with plus 2 sigma 2. Hopefully that makes sense. So that is our first order condition for agent number 1, which is going to be equal to 0. If we do the same thing for agent number 2 now, this means that we will have to partially differentiate the utility function with respect to sigma 2. If we highlight all the terms which involve sigma 2, we have this term, these terms, and also this term over here. if we begin by partially differentiating this row, we get eta minus r sigma 2 minus mu sigma 2 minus sigma 3 plus mu sigma 1 minus sigma 2. And if we now move on to differentiating this, this should also be a negative sign. Yep. If we go on to differentiating this, we will get plus mu sigma 2 minus mu, bracket sigma 2 minus sigma 3. And if we go on to differentiating this, we get plus mu sigma 1 minus sigma 2. Hopefully you can follow that. If we now collect all the like terms, we get minus 4 lots of mu sigma 2 plus 2 lots of sigma, 2 lots of mu sigma 1, and then plus 2 lots of mu sigma 3. Cool. So we get eta minus r sigma 2 minus 4 mu sigma 2 plus 2 mu sigma 1 plus 2 mu sigma 3, which is going to be equal to 0. And finally, if we do the same thing to work out the first order conditions for agent 3, we will have to partially differentiate the utility function with respect to sigma 3. And that is going to involve the terms, so these 5 terms. If we begin by differentiating these 4 terms first, we get this. If we now expand and collect all the like terms, we are left behind with this. And so this is our first order condition for agent 3, which will be equal to 0. Part B is now telling us to find a solution to the first order conditions and comment briefly on the interpretation of the result. Cool. So if we now just rewrite the first order conditions, and I'm just going to move all of these to the other side so they're all equal to eta. We get eta is equal to r sigma 1 plus 3 mu sigma 1 minus 2 mu sigma 2. Doing the same for the first order condition for agent 2, we get... Right, so we get this. This equation I will rewrite as brackets r plus 3 mu sigma 1 minus 2 mu sigma 2 is equal to eta. And this equation I will rewrite as minus 2 mu sigma 1 plus r plus 4 mu sigma 2 minus 2 mu sigma 3 is equal to eta. And then finally, this we can rewrite as minus 2 mu sigma 2 plus r plus 3 mu sigma 3 is equal to eta. Okay, now that we have these 3 equations, I'm going to write them in a matrix. So we have r plus 3 mu minus 2 mu and then 0 because there's no sigma 3 term, and then minus 2 mu r plus 4 mu and minus 2 mu and then 0 minus 2 mu and r plus 3 mu. So this matrix multiplied by the vector sigma, which is just sigma 1, sigma 2, and sigma 3, should be equal to eta. Cool. Okay, in order to work out what the vector sigma, which is sigma 1, sigma 2, and sigma 3 is going to be, we need to work out the inverse of this matrix, which I'm going to call M, and then multiply that inverse by this vector. So to work out the inverse of M, I'm first going to work out the matrix of minors, which just means if I want the matrix of minor for that element, I would cross out this row, sorry, this column and this row, and work out the determinant of the matrix that is left behind. And when I do that, I get r plus 4 mu multiplied by r plus 3 mu minus 4 mu squared. Doing that for the second element, I get 2 mu r plus 3 mu, and then 4 mu squared, and 2 mu r plus 3 mu, r plus 3 mu squared, 2 mu r plus 3 mu, sorry, these should be minuses, and then 4 mu squared, and then minus 2 mu r plus 3 mu, and finally r plus 4 mu r plus 3 mu minus 4 mu squared. So this is our matrix of minors. Next up is to find the matrix of cofactors, and what that means is just changing some signs according to this matrix. So if we add a negative to this element, it's now going to become positive, and same over here, same over here, and same over here, and the rest of the matrix stays the same. Next up is to now transpose this matrix, and as this matrix is a symmetric matrix, that isn't going to do anything. So last step is just to times this matrix by the determinant of M. So if we work out the determinant of M, we get r plus 3 mu squared, and then multiplied by r4 mu minus 4 mu squared, r plus 3 mu plus 4 mu squared, r plus 3 mu. And that's just me doing this diagonal multiplied together, this diagonal multiplied together, which is 0, and then this, which is 0. And then we subtract that from this diagonal multiplied together, which is 0, then this diagonal, and then this diagonal. Cool, so we get this. What I'm now going to do is just factorize out r plus 3 mu as it's present everywhere, and we get r plus 3 mu r plus 4 mu minus 4 mu squared plus 4 mu squared. And so expanding the brackets, we get r squared plus 7 mu plus 12 mu squared. This should be 7 r mu, and then minus it by 8 mu squared. And so finally the determinant of the matrix is r plus 3 mu brackets r squared plus 7 r mu plus 4 mu squared. So the inverse of this matrix is 1 over r plus 3 mu brackets r squared plus 7 r mu plus 4 mu squared, and then the matrix that we found out before, which is r plus 4 mu r plus 3 mu minus 4 mu squared. Cool, so this is our inverse matrix. Now we will times this matrix by eta, and hopefully you can see that is going to give us eta, and in brackets r plus 4 mu r plus 3 mu minus 4 mu squared plus 2 mu r plus 3 mu plus 4 mu squared, and close the bracket. Because when we times this matrix by eta, we're basically timesing every single one of these elements by eta, so we can just factorize out that eta. Hopefully that makes sense. Doing that to the second row, we get this, and lastly doing the same to the last row, we get this. So hopefully we can see that we can cancel out the 4 mu squares, and what that allows us to do is now factorize further the r plus 3 mu. So we have 8 on the outside and r plus 3 mu, and that leaves inside the bracket r plus 4 mu plus 2 mu. And we can do the same for this matrix, and this should be 3 mu squared. And that gives us 2 mu plus r plus 3 mu plus 2 mu. And lastly, doing the same for the last row. And once again, this should be r plus 3 mu. We get 2 mu plus r plus 3 mu. And so sigma 1, sigma 2, and sigma 3 is equal to eta r plus 3 mu. And therefore, we get 1 over the determinant, which was r plus 3 mu brackets r squared plus 7r mu plus 4 mu squared, multiplied by eta r plus 3 mu, r plus 6 mu, eta r plus 3 mu, 7 mu. So we get this. Hopefully you can see that we can cancel out the r plus 3 mu, and so finally we get sigma 1 as eta r plus 6 mu all over r squared plus 7 r mu plus 4 mu squared. Sigma 2 is equal to eta r plus 7 mu all over r squared plus 7 r mu plus 4 mu squared. And sigma 3 is equal to r plus 6 mu eta and r squared plus 7 r mu plus 4 mu squared. Cool. Just as an interpretation of the result, we can say that agent 1 and agent 3 will always have the same opinion, as sigma 1 is equal to sigma 3. Part C is telling us to calculate the Hessian undetermined nature of the solution you found under B. Cool. So the Hessian is just the second order derivatives, which means that we are going to look back at first order conditions and just differentiate them again with respect to sigma 1, sigma 2, and sigma 3. If we look over here, if we differentiate this with respect to sigma 1, we just get r plus 3 mu. Differentiating this with respect to sigma 2 gives us minus 2 mu. And differentiating this with respect to sigma 3 is just 0. Differentiating this with respect to sigma 1 is just minus 2 mu. Then we get r plus 4 mu and minus 2 mu. Hopefully you can see the pattern. Cool, so we just get this matrix. Okay, in order to determine the nature of our solution, we can either work out eigenvalues or we can use the principal minors method. In this case, I believe that the principal minors method is going to be easiest. So if we look at the determinant of this matrix J, but J1, by that what I mean is just J, but just that first 1 by 1 submatrix. So that is just going to be r plus 3 mu. If we now look at det J of 2, we get this 2 by 2 matrix. So if we work out the determinant, we have r plus 3 mu, r plus 4 mu minus 4 mu squared. When we expand this out, we get r squared plus 7r mu plus 8 mu squared. And then finally, if we look at the determinant of this whole matrix, luckily we did work it out before, it was r plus 3 mu, r squared plus 7 r mu plus 4 mu squared. Now, when it comes to the principal minors method, when it comes to the principal minors method, if all of the determinants, which I'll just write as Jn, is greater than 0, then we will have a minimum. If the signs alternate, that means we have a maximum. In this case, we can see that all of these will be greater than 0, as r and mu are both greater than 0. As a result, we have a minimum. Cool. Hopefully that all made sense.